Okay, so welcome to this DaSCI seminar that will focus on machine learning and climate change. First of all, I want to thank Professor Rolnick for very kindly accepting our invitation. David Rolnick is an assistant professor and Canada CIFAR AI chair in the School of Computer Science at McGill University and at Mila, Quebec AI Institute. He is a co-founder and chair of Climate Change AI and serves as scientific co-director of sustainability in the digital age. Dr. Rolnick received his PhD in applied mathematics from MIT. He's a former NSF Mathematical Sciences postdoctoral research fellow, NSF graduate research fellow, and Fulbright scholar, and was named to the MIT Technology Review's 2021 list of 35 innovators under 35. In today's seminar, Professor Rolnick will explore opportunities and challenges in AI for climate, from optimizing electrical grids to monitoring crop yield, and how methodological innovations in machine learning can be driven by impactful climate-relevant problems. Again, thank you very, very much for accepting our invitation. And whenever you're ready, the floor is yours.
Thank you. Thank you so much for the introduction. It's a pleasure to be here. Please feel free to interject with questions, especially in the chat, if anything is unclear, and hopefully there'll be a bunch of time for a discussion at the end too. So I don't think the problem of climate change needs very much introduction. We're increasingly seeing its effects across the world, everything from hotter summers in many places, severe droughts, severe fires. We saw this year catastrophic droughts in much of Europe, in the Western United States, in East Africa, and in China, at the same time as catastrophic floods in Pakistan and Korea. And these effects are becoming both more frequent and more severe. It's also worth noting that climate change has a disproportionate impact on already disadvantaged communities. It serves to exacerbate existing societal inequities. And often the places that climate change hits the most are those that have also done the least to cause it. So climate change is caused by greenhouse gas emissions, carbon dioxide, methane, nitrous oxide, and some others. And the UN's Intergovernmental Panel on Climate Change, IPCC, has said we need net zero greenhouse gas emissions by 2050 if we are to avert the most catastrophic impacts of climate change. There are several things that are needed, though, because even with net zero greenhouse gas emissions by 2050, which we are not on track for at all, we need to recognize that climate change is already killing people and it will kill many more. We get to decide how bad it is, and we get to respond as well as possible, given that it is already happening and will continue to happen to some degree, whatever we do. So action encompasses both mitigation, that means reducing greenhouse gas emissions, and adaptation, which is resilience to the consequences of climate change. And again, it's important to remember climate change is not an on-off switch. We get to decide how bad it is. So I'm going to be starting out by giving a framework for how to think about how machine learning tools can play into climate action. This comes from a paper that a number of us wrote called Tackling Climate Change with Machine Learning, which looks at many different areas of application for machine learning, from electricity systems to forestry and agriculture to buildings and cities, transportation, heavy industry, climate modeling and prediction, and so on. And across these various different areas of application, we saw a number of themes, which I want to touch on with a few examples. If you are interested in more detail, I do encourage you to check out the full paper. So the themes that I want to touch on, which I will then go into examples from my own research group. First of all, improving operational efficiency. There are many settings in which there is a complex automated system that machine learning can help run more efficiently. So for example, that could be optimizing the heating and cooling system, HVAC, within a building. This is already done in smart thermostats, in personal homes, but it's also increasingly being done in industrial settings and in commercial buildings, which require a lot more sophisticated algorithms to control the temperature efficiently. So machine learning is being very useful in such contexts. And similarly, in a lot of industrial processes where there are many processes that require energy or otherwise produce emissions that can be made more efficient. For example, steel and cement manufactured together accounts for over 10% of all global greenhouse gas emissions, just steel and cement. And making those manufacturing processes more energy efficient can be very valuable. Now, I do want to mention here that improving efficiency really matters what you're optimizing for. So if you're optimizing for cost, that's not always the same thing as optimizing for reduced energy or reduced greenhouse gas emissions. You might be in a setting where, for example, the dominant factor in cost is not energy, it is human labor. And so you might actually increase energy consumed if you're optimizing purely for cost. So again, this is one of those settings where you really want to make sure you know what you're asking for. If you optimize for one thing, it's not necessarily the same as if you're optimizing for a different objective function. Second theme that I want to touch on is in gathering information. Here one might take satellite imagery or large textual corpora and use machine learning to pick out important information from within that raw data. So for example, you might take computer vision algorithms and pinpoint deforestation from satellite imagery. Here's some satellite imagery. You can see a bunch of deforestation happening. I think this is Bolivia. And you can also more precisely estimate carbon stock, the amount of carbon stored in a piece of land. Why do you need to track deforestation and estimate carbon stock? Well, it helps in shaping policies surrounding land use. It helps in enforcement of certain regulations surrounding forest custody, and it helps in incentivizing landowners, in verifying that they are conserving their land if there are carbon pricing systems, for example. For all of these reasons, it's really important to have very solid information about how land is being preserved and how much carbon is stored in it. And machine learning can help scale that up in a way that a human wouldn't necessarily be able to do nearly as fast. Similarly, for large textual corpora, NLP is being used, for example, to parse through corporate financial disclosures to find relevant information, say where a company feels its risks are as a result of climate change, because sometimes there's too much text to go through manually. Forecasting is another application where we see machine learning being useful. Here are a couple of examples from balancing the electrical grid. It's important when you're running an electrical grid to make sure that the amount of power available equals the amount of power consumed at any given point in time. And this means you need to know how much power is available and how much power is needed. And so it's important to forecast both the electricity supply and the electricity demand. The supply is actually pretty tricky sometimes. In the past, we relied primarily on fossil fuels, which are what's called controllable generators. So if you have, for example, a natural gas or a coal power plant, you can change how much power is being produced to meet the demand. However, that's not necessarily the case with solar and wind power, where the amount of power available depends upon how much the sun is shining or the wind is blowing. And then for hydropower, depending upon the hydropower station, it can be one or the other. So the need for forecasting electricity supply is actually growing more and more as we use more solar and wind power. So this is becoming even more important. And predicting demand is also really important, again, to make sure that you have enough supply to meet demand at any given point in time. You aren't overproducing electricity and wasting it, or actually running the risk of a blackout. So machine learning is being used in both these cases with time series data, sometimes with computer vision as well. For example, if you're trying to work out how much solar power is available, you might want some pictures of the clouds in the area at the given moment. Predicting demand, the UK's national grid recently introduced machine learning algorithms and actually cut the error rate for predicting demand in half. So there's a lot of scope for improvement in some of these industrial systems. Speeding up simulations. I'm often asked if machine learning could just simulate the entire Earth's climate. And sort of, but we have very good physics-based models for the whole Earth's climate. We don't need machine learning to go in and just model climate change from scratch. We already know how the climate is changing, and the physics is much more complicated than machine learning would really be able to simulate in many cases. However, sometimes the physics is very slow. And so there can be a utility in having machine learning help speed up simulations that may be based upon exact physics, where the physics is correct, but the simulations are too slow. Climate models might take months to run, even on supercomputers. And so taking pieces of them in particular that are very slow and speeding those up it can be very valuable. Likewise, in other contexts like aerodynamics of vehicles, where again, we have very slow physics-based simulations, or in simulations of the electrical grid planning models, which again rely upon physics and might be too slow to run exactly. And then the final theme that I want to touch on is accelerating scientific discovery. So here, the goal is to speed up the experimentation process in context where we need next generation climate tech. This could be often in materials design, for example, in design of new materials for batteries, which still need to be improved a lot, or in solar perovskites, which are used in solar cells, or carbon capture sorbents potentially, though I'm not sure that people are doing that yet. A bunch of other different contexts. And here, what the machine learning is doing is it's learning from past experiments, what materials were good when they were tried in the past, and suggesting new experiments to try. This is also being done in drug discovery, by the way. Learning from past experiments to suggest new promising experiments. This is not replacing physical experimentation, but it's suggesting new materials that you might try, or new experimental protocols for working with those materials. So for example, machine learning has been used for designing better charging protocols for electric vehicle batteries that make them more last longer, be more effective. Okay, so now we touched on these overall themes. I want to highlight some, go into more detail in some examples on these various different points. So but before I get into that, I want to look at some overarching points that we see across these different themes. So first of all, thinking about how machine learning is not just beneficial for climate action, it goes the other way around as well. Looking at these kinds of climate relevant problems actually offers opportunities for cutting edge machine learning innovation itself. Across a number of different areas. Hybrid physical models turns up again and again, integrating physics-based knowledge or other kinds of domain-relevant constraints into machine learning systems. Really valuable. And very tough currently. Oftentimes, machine learning is very difficult in particular deep learning, oftentimes very difficult to integrate domain knowledge into the algorithms. Transfer learning and meta learning. As we'll see later, oftentimes there are reasons why you need to generalize from one set of data to another set of data, and there might be very imbalanced data across different regimes. And so transfer learning and meta learning techniques can be very valuable. Interpretable and causal machine learning. Oftentimes, if machine learning is producing some kind of output that's going to be used, for example, by policymakers or by other people who are implementing some decision on the basis of the machine learning algorithm, it can be important to have that machine learning explain what is going on under the hood, and ideally provide some causal reasoning as well, though that is maybe a little bit further out. Uncertainty quantification is also really important. Again, in a decision-making context, you would want to know how confident you are in a prediction or what sources of uncertainty are. And many other areas of machine learning research are really valuable. And these climate relevant problems offer fantastic test beds for working on these kinds of questions. And as we'll see in the examples later on, by thinking very deeply about what is needed within a particular problem space, you can actually really push the envelope on what's possible methodologically. Of course, it is worth bearing in mind that not every climate problem requires cutting-edge machine learning. Sometimes simple methods are sufficient, and it's always worth starting out with the simplest methods. Random forests are going to be better than transformers if both of them work, because people will be more able to use random forests. They have a lower barrier to entry. Simpler technologies are just better if they work. As a good strategy, which I use in my own group, think about picking, if you are interested in machine learning innovation, pick a problem that you suspect may need innovation, but then still start out with simple baselines, because sometimes those will be sufficient, and that's great if that's the case. And then, or work on a problem where you think just an out-of-the-box convolutional neural network is going to work. That's fantastic. That's really helpful in actually solving meaningful problems. Some considerations overall. Machine learning is not a silver bullet. It's not magically going to solve climate change. It's only relevant in certain situations. And even in those cases, it's only one piece of the answer. It's always machine learning to help do whatever was being done already, to work together with the people who are working on this problem and really serve whatever their interests are. Machine learning is not sufficient in itself to solve any one of these problems. High impact applications of machine learning are often not flashy. For example, self-driving cars get a lot of press, but finding failures in railways is more important. Predictive maintenance on railroads is being done by Deutsche Bahn, for example. It's much more impactful from a climate perspective. Self-driving cars are actually probably going to make climate change worse, which we'll see later on. Remember that the things that get talked about a lot are not necessarily, at least from a climate perspective, necessarily the biggest impact. Interdisciplinary collaboration is key. One cannot work on any of these problems without interfacing very closely with people in the relevant domain. And that means both researchers and also stakeholders who will be using and affected by the technology. Ultimately, something isn't impactful unless it's used, and it's not used unless it's solving the problem that people need to be solved. So first of all, you need to work to scope the right problems, make sure you are actually solving the problems that people need. So it's important to make sure that you're working with relevant stakeholders right from the start to make sure you're solving the right problems. It's also important to incorporate relevant domain information to make sure that you are not losing some information that could be very valuable to simplify your task. And it's important in shaping pathways to impact. As fantastic as a NeurIPS or ICML paper is for a machine learning research project, that is not actually typically how one ensures that the project has impact. That is just one step. And so making sure that one is actually connected to the stakeholders that will use the tool that you develop and will build in any design choices that are necessary for that use right from the start, that is really important. I also want to highlight equity considerations. The who, what, and how of how problems are being worked on. Obviously, there are extreme imbalances in the set of stakeholders that are empowered to work traditionally on AI problems overall. And these kinds of imbalances are very much the case still in AI applied to climate relevant applications. As a result of differences in funding across geographies and institutions, differences in access to compute, straight out biases, racism, and other factors that cause a much more limited set of voices to be empowered in AI and AI for climate that then is both equitable and is best from an impact perspective. This takes active work at every level. One of the reasons why this is absolutely terrible, only one of the reasons, is that it also affects the problems that get worked on. For example, we see that I've seen that a lot more energy gets devoted, or at least a lot more publicity gets devoted to AI for, say, fighting wildfires than for fighting locust outbreaks or melting glaciers. And that's potentially because these are all of them problems caused by climate change, but wildfires primarily affect North America, Europe, and Australia. Locusts primarily affect East Africa, the Middle East, and India. And these problems should both be worked on. But there is a difference in funding and resources available to stakeholders who care about these different issues. So be careful of this when you're selecting and prioritizing problems, recognizing that, of course, what one knows about and what one is personally involved in is going to affect the problems that you prioritize, but there are sometimes other problems that are also high priority. And then ensuring that data is representative. If you work with data from one geography or one set of communities, that may impact the applicability of your algorithm in a different context. It may not generalize very well. We'll see some examples. So I'd now like to turn to some examples from within these various different themes that I highlighted. First of all, looking at improving operational efficiency. So let's look at an example from optimizing the electrical grid. And the context for this is that balancing the electrical grid, which means deciding how much power to produce across the grid to meet demand, requires solving a big non-convex optimization problem, which is called AC optimal power flow. Now, this is, as you know, computer scientists will recognize, non-convex optimization problems are hard to solve. This is what this one looks like. It is quadratic, actually, but it is non-convex quadratic. So there is no neat way to solve this. And in practice, since exact solutions take too long, typically electrical grid operators simplify the problem, they actually linearize it. And in the process, they waste large amounts of power. This is especially true with solar and wind energy, since the constraints in the problem actually depend upon how much power is available at a given generator. And therefore, the problem needs to be resolved as the amount of power available changes, which can be every few minutes for solar and wind. So what does one do? Well, we have worked to design deep learning algorithms that can actually approximately solve such a non-convex optimization problem. But the important thing here to bear in mind is that it's really important to satisfy the constraints in the problem. These constraints correspond to the flow of electrical power within the grid. And if you violate the constraints, then you cause the grid to go down. You cause a blackout because there isn't enough electrical power to meet demand and everything fails. So the reason why people have done these simplifications is because it is more important to make sure you don't violate the constraints than to make sure you get the exact optimum. And previous deep learning approaches haven't been able to do this. Sort of the naive way you might go about this is you would try to minimize this with a penalty for violating your constraints. This is a soft loss approach. You have a penalty if you go too far away from the constraints. This does not work because that means that you end up trading off between your objective function and your constraints. But you cannot violate your constraints at all. And so these naive approaches, as we'll see, fail. And you need an approach that actually builds the constraints in, making sure you're not violating the constraints. Okay, so how do you actually frame this problem? This is work, by the way, from iClear 2021. and done together with Priya Donti, shown here, and Zico Coulter. So this, the way we frame the problem is as an approximate mapping from problem parameters X to solutions Y. And you have a family of optimization problems parameterized in both the objective function and in the constraints by X. And you would like to minimize the objective function while satisfying both the inequality and equality constraints. Okay. You're given an X and you want to find the minimum Y. Okay, so how do we do this? The overall overview, which I'll dive into in more detail in a moment, is that you take in your input X, you throw it into a neural network, you output a partial solution, you then complete it to get a full set of variables, and then you then correct it to make sure it doesn't violate the inequality constraints, and then you train the entire thing end to end. Let's look at each component. First component, we output a partial set of variables. Why do we do this? Well, if you were working with equality constraints, some of the variables are in some sense determined, they aren't free, based upon the variables that you've already selected. You have only a certain number of degrees of freedom because you are constrained to lie within the manifold given by your equality constraint. Now, once you've output a subset of the variables, you can then solve for the rest using the equality constraints. You could do this in a number of different ways, depending upon the problem that you're working with. In our case, we can't actually solve in closed form for the other variables, so we have to use something like Newton's method to get the other variables. Now, you may notice that if you are trying to train this entire thing end to end, you'll need gradients to propagate through here. You'll need backpropagation to work. And we can actually compute the relevant gradients by using the implicit function theorem to implicitly differentiate the variables that we're solving for using Newton's method with respect to the other variables. Okay, now we've got a complete set of variables that by definition satisfies the equality constraints. And now we can try to satisfy the inequality constraints. And what we're going to do is within this green manifold, which represents the equality constraints, we're going to move towards the blue subset, which represents satisfaction of the inequality constraints. And we're going to do this using gradient descent according to the inequality constraints, so moving closer towards satisfying them. And this is, in practice, going to take only a few steps just to get inside this blue region. And we do it by moving within the green region, so along the manifold defined by the equality constraint. For those who are worried about differentiating through this, don't worry, the gradient descent is not with respect to the model parameters, so you don't have to ever do a Hessian computation. It is just with respect to the output vector y, so there's no double derivative ever being taken. Now we train the entire thing end to end to minimize the objective function, which of course is what we want to do, and also to minimize any deviation that managed to get through with the equality or the inequality constraints, even though this is just to help it learn at the start. And so combining all of these things, the completion step to get all the variables, the correction step to make sure they satisfy the inequality as well as the equality constraints, and the through training using the soft loss, we are able to effectively solve non-convex optimization problems. We test this in a bunch of different circumstances: convex quadratic programs, which there are traditional solvers for, simple non-convex versions of that. So if you swap out this linear term for a trig term, then you break all the normal convex solvers, but our method still works fine. But then the problem that we actually were interested in was AC optimal paraflow. And so we look at real plausible test cases from the IEEE test cases, and we see that we're actually able to perform really well on AC optimal paraflow. Our method is shown here in blue. The top is the classical optimizer. And let's go through some of the baselines. Here we have a neural network trained using the soft loss alone, so just trying to minimize deviation from the constraints. And you see it violates the constraints very heavily, not at all feasible. Same with a supervised learning approach, where you ask it to replicate the behavior observed at various example pairs. That doesn't work either. You still get a significant inequality violation in this case. Even if we add in our correction procedure, it still doesn't fix things. Here we tried various ablations of our model, getting rid of completion, correction, soft loss, and other things. And we find that all of these are very useful for making the model work. And then we can compare against the actual optimizer, which has basically the same objective value, but is 10 times slower. And actually, in practice, we expect it to be about 100 times slower on this size of problem, and even slower on bigger problems, because we were assuming no parallelization, but actually our model parallelizes very naturally using a GPU because it's a deep learning based model, whereas the classical optimizer doesn't do that. So 10 to actually 100 times faster than the optimizer with a very small 0.2% optimality gap, and it satisfies all the constraints, unlike other deep learning. Okay. Now let's look at the second example that I want to give, which addresses both the gathering information and the forecasting tasks, because it's doing both of these things in different settings. So the overall motivation here is that it's important to gather more data on agriculture as we try to respond to climate change, because climate change threatens food worldwide by extreme weather causing crops to fail periodically in across different geographies and in different ways. And so mapping crops and forecasting crop yield are really important to averting food insecurity. However, the data involved are sparse, they're only found in certain locations, and they're imbalanced across those locations and also across different crop types. So for example, here we can see the world. This is a data set from NASA, which is our partner here. This is the crop harvest data set, and the blue points show where there's information about whether something is a crop or not a crop. It's a very, very small amount of information. Orange points show that we know what the crop is. So maybe this is wheat. But in most cases, you can see we don't have any appreciable amount of data on what the crop is. And in some places, we don't even know whether it's a crop or not. So we'd like to be able to have algorithms that perform well across the whole world, but we only have this kind of patchy data. So how do we deal with this? Well, we develop meta-learning algorithms that can generalize fast to new locations in predicting crop yield and labeling crops. Some background quickly on meta-learning, for those who haven't encountered it before. Meta-learning refers to learning in such a way that the model can adapt quickly to a new task given some new data, but not very much new data. Often people work with MAML, model-agnostic meta-learning, which is a framework for training a neural network to maximize the effectiveness of gradient updates on new tasks. So what you're doing essentially is you're moving your model parameters theta in such a way that you have brought them to a point in parameter space where an update on a new task gives you one of several different parameter settings, which would be tailored to whatever that task is. So in task 1, you might go to theta star 1, task 2, you might go to theta star 2, task 3, you might go to theta star 3, and you don't know what your task is in advance that you're going to have to adapt to. So you want to be close to all these parameter settings and be able to move to them very fast using a gradient update, several gradient updates. So MAML is a training paradigm. It can work across different neural network architectures and different tasks. We build on MAML. Specifically, we introduce a task-informed meta-learning framework. And there are two components to what we do here. The motivation really is that you have some extra data if you're trying to generalize to a new location or crop type, or more generally, if you're trying to generalize to a new task. In many cases, you have some task metadata. You know something oftentimes about what the new task is. You might know that you've seen coffee in Brazil and maize in Kenya, but you've never seen maize in Brazil or coffee in Kenya. And so you would like to take the information you knew about your previous tasks and be able to leverage it when you're learning a new task so that you don't need as much data to learn that new task. And so that's exactly what we do. We take this task metadata, which has previously been ignored in meta-learning. And in this case, it's lat long information and also crop type, but that can be anything depending upon your setting. And we use it to modulate the hidden representations in the meta-learning. So here we actually have two neural networks. We have a task encoder, which is a simple neural network, which produces these vectors to modulate our hidden representations within a mammal model. So this is the mammal model, and this is the within the outer loop optimization of mammal, we have this other network that modulates the representations within mammal. The second component that we add here is, since the data are often very imbalanced, we want to make sure that we don't overfit to particular data. So we drop from training any data where the model is starting to memorize it. So if it starts performing almost perfectly on something, we remove that from training for the rest of the training regimen. This is called forgetfulness. We call this forgetfulness, and these two ingredients turn out to be really valuable in generalizing in settings where we have task metadata. So let's quickly look at some results. Here we've compared TIML, task-informed meta-learning, our approach, and various variations of it to different baselines. Random forest approach, mammal approach on the other hand, and then various other things which are intermediate, like crop pre-training. So we've just pre-trained, but we haven't actually used a meta-learn. And so we find that across all these tasks, and overall, TIML just performs much better. In particular, on the Brazil task, which is a particularly challenging one, we just blow everything else out of the water. You can see the F1 score and also the AUC ROC score are just so much better than everything else. And something that I'm particularly excited about is that our model performs particularly well on very small data sets. So if you are generalizing to a new task and you have very, very limited data, you would like to still be able to learn, but most models fail. They need a much larger number of new samples in your new task. So here, in particular on the Togo task, you can see that TIML, the blue line, is performing just as well, basically, even with smaller training sample sizes. It's a little bit less good, but it's only a little bit less. Whereas these other models, including mammal, really drop off as you decay the amount of data that you're giving them. Okay. And one more thing that I want to highlight here is it's actually very broadly generalizable. We previously saw this on a classification task. Now we can see it on a regression task. This is crop yield prediction. It's a forecasting task, and it's dealing with time series. And here we can see that across different architectures, with both an LSTM and a convolutional neural network, TIML is really valuable. It manages to improve over the baseline in both the LSTM and the CNN settings. And again, this is a regression task. We previously saw a classification task. It's very broadly applicable. We also ran it on a classic machine learning test case of omniglot and similarly beat all the other algorithms in generalizing to new alphabets. Let's move on to another theme, speeding up simulations. I'll go through this pretty quickly. Here, our motivation is that, as I mentioned before, climate models can sometimes have slow pieces that really cause you to have to take a very long time to run a climate simulation. And one of these particularly slow pieces is radiative transfer, how radiation passes through or is absorbed by layers in the atmosphere. This is sort of what it looks like. Radiation comes in from the sun. Some of it hits the Earth and is absorbed. Some of it is re-emitted into the atmosphere. And then some of it gets absorbed by the atmosphere. Some of it gets sent out into space. The balance between these different things is actually what causes climate change, or the imbalance, I should say. It's time intensive to compute this using exact physics. And so people use various heuristics. Such bottlenecks, however, mean that climate models often have to be run at very high resolution. For example, a grid scale of hundreds of kilometers might be typical. So you don't have very local information about how your climate model, or weather models similarly are often very high resolution. And this can impede local and regional responses to climate change because you don't have as granular information about what is going to change where. So we use deep learning to rapidly approximate rapid radiative transfer calculations. This is work led by my students Zava Huilen-Kachai and Venkatesh Ramesh, together with partners in Environment and Climate Change Canada, which is the Canadian agency responsible for climate modeling. And we do a bunch of different things. First of all, we actually provide a data set, a benchmark data set, which is designed to catalyze work in the future. This was published, by the way, last year's NERPS. That data set is based upon data from the real Canadian Earth system model and includes, in particular, OOD test sets, out of distribution testing. One of the critical things to test with climate modeling is, does it generalize to different climate settings? Like, does it generalize to the future where the climate is going to be very different? So we include a test set for that. We include also pre-industrial conditions, so where there were different concentrations, for example, of CO2 in the atmosphere, and right after a big volcanic eruption, where the Earth's climate looked very different in 1991, with the eruption of Mount Pinatubo. And we throw in different physics quantities, gas concentrations, temperature, pressure, humidity, etc., different layers and levels of the atmosphere as input to the neural network. And we're trying to predict something called the up and downwelling flux, both short and long wave radiation. If you don't know what that is, doesn't matter, and heating rates per layer of the atmosphere. So we have a column of atmosphere, and we have information about gases and humidity and stuff like that at each layer in the atmosphere, and we're trying to work out how the radiation passes through every bit of that. And so we use both fully connected neural networks and more structured approaches like one-dimensional convnets, because it is a one-dimensional column, various graph neural networks, and we also use transformers. And we find that the structure of the convnets and the graph neural networks allows us to generalize better in the out-of-distribution test set. So you can see that all of the models perform very, very well on the data that they were trained on. But if you go back to the past, or particularly out to the future, you really need some of the structure of the convnets and the graph neural networks in order to get the better performance. And actually, our models are performing so well that they're currently being tested for integration into the Canadian climate model, the Canadian Earth system model. We're also working on this final bullet, but I don't really have time to go into it. We're working on accelerating the design of new catalysts for green energy applications. I'm happy to talk about that separately. So while I've talked about these overall themes, I want to highlight that there are other some bigger picture considerations of how to think about the space of climate change and machine learning. And first of all, throughout all of these examples, I've talked about the importance of really integrating one's models with domain-specific information. And now I want to talk about what happens if you don't do that. And so to do that, I'm going to talk about ImageNet. ImageNet is something that probably everyone here is familiar with. It's one of the most popular machine learning data sets, and machine learning continues to rely on data sets like ImageNet to evaluate models as well as to pre-train for real-world tasks. ImageNet 1K, which is the version of ImageNet that we're going to look at here, has 32,000 citations currently. Now, these data sets were often created from internet data, and they were typically chosen by computer scientists and annotated without relevant experts. So, for example, ImageNet was actually annotated by Amazon Mechanical Turk, people through that platform who didn't have particular expertise in doing these various things. Now, actually, 27% of ImageNet 1K is made up of images of wild animals. And so we worked with ecologists, experts in biodiversity, to analyze these images. ImageNet, it turns out, has a lot of biodiversity relevant images. So given how much it's being used, we wanted to understand how biodiversity and ecosystem monitoring were impacted potentially by the use of the image. This is work with Sasha Luciani, which we just put out. So first of all, we together with our ecologist partners looked at to what extent the data in ImageNet is actually correct. And we found that 12% of the images of wild animals in ImageNet are flat out wrong. Some of the classes are 90% wrong. These are some of the worst offenders. Black-footed ferret, 98% incorrect. Only 2% of the images were correct. The goldfinch, Cardulus cardulus, 90% incorrect. Only 1 in 10 of images of goldfinches were correct. And this varies a bunch across different groups of animals, with amphibians and reptiles being particularly poorly classified. So there are a bunch of sources there. First of all, the most glaring reason was because the people creating ImageNet didn't know anything about animals. And the annotators also didn't know anything about animals. And the internet doesn't always know much about animals. So none of the ways in which this data set was created were bringing in domain expertise, which was necessary. For remember, this is over a quarter of the data set. There were prevalence effects. Remember, this was internet data. It was pulled using Google image search. If you search for anything to do with ferrets, most of the images you get up on Google image search now, and I assume then as well, are images of people's pet ferrets, generally in cages or being held by people. And that is actually what ImageNet is. It's images of people's pet ferrets. By contrast, the black-footed ferret, which is specifically specified in ImageNet, is actually an endangered species that's rarely seen. And so, of course, not surprisingly, you get a lot of images of pet ferrets instead of this much rarer species. So in some extent, that maybe is expected. Nomenclature is another issue. Leaf beetle is, I forget, it's about 50% incorrect, I believe. And the reason for this is that when you do a search on Google for leaf beetle, you get beetles on leaves. Turns out that a leaf beetle is any beetle in the family Chrysomelidae, which is a specific thing. And the images that were pulled were not that specific thing. In fact, they were other kinds of beetles, but there are many other kinds of beetles even in ImageNet. And so you ended up with a situation where a large fraction of the leaf beetles were not only not correct, they were actually belonging to other classes in ImageNet, like the ladybug, which is another kind of beetle, which is often found on leaves. And so in this case, not only were the images wrong, they were actually correct for another class in ImageNet. 12% of classes conflict with other classes. So not only do the images sometimes conflict with other classes, sometimes the classes themselves do. For example, there are classes tusker and African elephant. A tusker is just an elephant with very long tusks. And almost all of them are African elephants. So everything in the class tusker could equally well be placed in the class African elephant. So in some sense, all of those images are wrong, or at least ambiguous. Similarly with meerkat, which is a kind of mongoose, even though these are two separate classes in ImageNet, meerkats are considered to be a separate group, even though all of those images could also be placed in the mongoose category. 11% of the classes are vague or unclear. For example, cricket or kite, where it's not clear what should belong in those classes according to the ecologists. And sometimes that means that it's not clear where images should go, whether they should go in this class or another class, for that reason as well. Oftentimes, the lack of clarity comes from geographic differences. A kite means a different thing depending upon where you are in the world. So that introduces, it brings us to our next point, which is geographic bias. We find that there's a huge bias in where the data is coming from. We analyze birds specifically because it's easy to, or more possible to identify birds to exact species. We find that 58% of the images show birds from the US, even though the US represents only 8% of total bird diversity. You can compare black, which is the true biodiversity across different regions, compared to ImageNet biodiversity. And this was the case in a bunch of different ways. Oh, sorry, Europe was also severely overrepresented. The imbalance is true for choice of species classes. So for example, the bald eagle is the only eagle in the data set. And that happens to be the national species, the national bird of the United States. Even though there are eagles which are also extremely important to cultures around the world. Mislabeled images is also a situation where there's imbalance. So for example, if you remember that goldfinch example, goldfinch was 90% incorrect. And most of that was because it was actually another species of bird that was found in the US. The goldfinch, which was supposed to be there, was actually the European goldfinch, the one that you're familiar with in Spain. but instead they put an American species in there because that was what most of the data were coming up for. And then maybe the most insidious way in which this turns up is in the images chosen to reflect a non-specific class. So for example, there's J. This is the J that you probably are familiar with. It's the Eurasian J. This is the J that we have in Canada and the US. This is one that's in Mexico, and this is one that's in China. Guess which one is in ImageNet? Well, 62% of the images in ImageNet are of this one, the one only found in the US and Canada. And there are 50 species of jays around the world. They look very different. If you're an algorithm trying to generalize, you're not going to be able to do that. And so secretly, even though this class is technically correct, the images are of jays, they're actually of US jays. And that's really curtailing the ability of the models to generalize across different geographies. So we see this really as a test bed for seeing problems in data sets overall, where here we can actually find out where an image is from because we know where birds are from. And we can find these kinds of biases very much more distinctly than we might be able to if it were like a chair, where we wouldn't necessarily know where the chair is from. There are also other issues. We have cultural bias. There are many more classes for mammals, which are only 6,000 species worldwide, compared with insects where there are 1 million species. So that's like people are more interested in mammals. I guess that makes sense. Then there's contextual bias, which gets a little bit more fishy, literally. Fish are generally shown dead across many species because people like fishing. And so this is a typical fish from the class tench. 62% of the images of tench, barracuda, coho, salmon, sturgeon, and gar are of people with dead fish that they've just caught. I would classify most of the images as a person. This is not mostly about a fish. Similarly with game animals, so often like antelope are shown dead with people with guns beside them. 5% of the images show multiple kinds of animals. So this is supposed to be a zebra, I think, but it's also a cow. And 1% of the images are fake animals, like this stuffed dugong. Very cute. 1% are image collages. Guess which one of the species is supposed to be represented here? It is this one. All of the other ones are different species, which all fall into other ImageNet classes. Okay, so this is what happens when you don't bring in domain expertise. And why does it matter? Well, it matters because accuracy on ImageNet depends upon classes being largely correct, and clearly this is not correct. People fight for like 0.1%. But some of the old people fight for tiny improvements in accuracy on ImageNet. And here we see that there's 12% of the images are flat out wrong. 12% of the classes could be equally well other classes. It's secretly testing few and zero-shot learning because the classes are actually imbalanced representations of much more diverse classes, geographically speaking. There's a huge danger in using ImageNet data to pre-train ML models for real-world tasks, especially those including biodiversity, since the original data set is hugely biased and just wrong. And then it points at broader failures in how machine learning data sets are often created by computer scientists, also in particular geographies, particularly institutions, often from internet data sets that are already heavily biased and typically annotated without relevant expertise. We really need systemic change in machine learning best practices for data set, but also algorithm creation and use, really building in domain expertise. By the way, this is a real image from the ImageNet data set. It is a wombat, which is an Australian animal, which is dressed in a dress with butterfly wings and with human hands. This is an example of the class wombat in ImageNet. And then finally, I want to touch on ways that machine learning can impact the climate that are not positive. There are many ways that machine learning is being used, and not all of them help climate change. The one that maybe gets talked about the most is computation-related impacts. There's energy involved in using, in training and in running at inference time a machine learning algorithm. And there are also embodied emissions from the hardware which we need to run it. Building a computer server takes carbon, takes energy. These can be big for certain models. It depends on whether you're using a really big model or something much smaller, how often you train it, because often training takes a lot more energy than inference time. But actually, these impacts are probably dwarfed by other impacts that aren't talked about as much. There are the immediate impacts of applications. Machine learning is being used in a lot of ways that directly harm the climate. So for example, it's used a lot in fossil fuel exploration and extraction. The fossil fuel industry is expected to make $500 billion in additional profit just by 2025, thanks to AI and advanced analytics. That's a lot of impact, and it's not, generally speaking, good impact. There are systemic impacts of applications as well. Maybe you don't work on machine learning for fossil fuel exploration or extraction, but a lot of machine learning is used for advertising systems, which are explicitly designed to increase consumption. That is doubtless having a significant but unmeasured effect upon how much emissions is consumed worldwide. And then there are a bunch of applications where the impact sort of depends upon how we build them. Self-driving cars. Now, autonomous vehicle technology can be used in a bunch of different ways, and I'm not here to say that it's bad, because it has various effects, like possibly improvements in public safety, depending upon how effective the technology is. But from a climate perspective, self-driving personal cars are probably bad, because they'll induce people to drive more by lowering the barrier to driving. Even if each mile driven gets a little bit more efficient, the impact is expected to be negative from a climate perspective. However, if self-driving technology is used for public transportation, potentially also for freight, though that's less clear, that can have a beneficial effect if it increases the amount that people use buses and the effectiveness of public transportation. So it really depends on how the technology is developed, the implicit decisions that we're making as technologists, whether we're working on the technology from the perspective of considering at least the climate impacts of how it's used or not. And this is what I want to end on by saying AI for good is a term that people throw around a lot, but it doesn't mean just adding new good applications of AI on top of business as usual. It means shaping all applications of AI and machine learning to be better for society. And the implicit choices that we make as technologists matter, as well as the explicit ones. So that's what I want to leave you with. But in conclusion, I do also want to leave up some additional resources for finding out more about this space. As mentioned, I am one of the co-founders of Climate Change AI, which is a global nonprofit that catalyzes impactful work at the intersection of climate change and machine learning. We wrote that Tackling Climate Change with Machine Learning paper, and we do a bunch of other stuff. We have a lot of digital resources, that report, but a lot of other ones, including ones aimed at policymakers and other audiences. We have a new community-driven wiki with datasets and additional resources listed. We run conferences and events. Our NeurIPS workshop is just coming up in December. You can attend that virtually. And we have events pretty regularly. We also have a symposium at AAAI coming up in just a few weeks. We have mentorship programs for our workshops. So look out for the next one, I guess. You can't submit to NeurIPS, the NeurIPS workshop anymore. The submissions have closed, but for our next workshop, do keep an eye out for that. And you can look at our past papers at this link. The summer school, Climate Change AI, will be opening for applications soon. We have different tracks for people with AI experience and for people with a climate relevant experience. We also have funding programs. We have an innovation grants program that last year gave out $2 million to projects at the intersection of climate change and AI. Stay tuned for an announcement on this coming round. We also have resources for connecting more broadly with the community. We have a digital platform at community.climatechange.ai. We have a newsletter which comes out every month with jobs, funding, data sets, other opportunities to bear in mind at this intersection. It collates lots of information in the overall space. And we have a blog as well for that kind of purpose as well. We have monthly webinars and bi-weekly happy hours and lots more at our website. So I'll leave you with that, and I'm very much looking forward to the discussion now. Thank you.
Well, thank you very much for this amazing talk. I really enjoyed it. And now, well, it's time for questions. So as usual, please, you can write your name in the chat, and I'll give you the turn to speak. So now it's time for questions. Don't be shy. Any questions? Okay, so Carlos Peláez, please go ahead.
Hi. I just want hi. Thank you for the meeting. It was very interesting. I wasn't expecting the part of the ImageNet, and that was very curious because I am computer vision researcher, so I am very familiar with it. Can you can you listen to me?
Yeah,
Yeah, sure.
Oh, okay, okay. So sorry, my question is, what of the fields you explained before, would you say it is the more interesting, the one who impacts more in the near world?
I think that they're all very impactful. I only brought up impactful applications, and I would really watch out for a framing of let me work on the most impactful problem, because there are so many impactful problems in this space. What should dictate what you work on should be what your tools are and what you're interested in, and maybe where you have partnerships or knowledge of the area. So maybe you're interested in agriculture, maybe you're interested in monitoring biodiversity. Though don't monitor biodiversity by working on ImageNet. There are a lot of other very good data sets that focus on wildlife and do a much better job. The particular problem that one should work on really depends upon the setting. I would not feel like you have to work on the application, because what we need is people working on all of these things. And sure, don't work on something that's really low impact. I once had somebody suggest working on machine learning for getting people to buy more indoor plants. Don't work on that, because indoor plants are not a major factor in climate change. But you could work on any of these problems and it would be extremely useful.
Oh, okay, yeah, I understand that. It makes sense to me. Another question, if you let me.
Please.
Yeah, sure.
Thank you. I was wondering because a few years ago, I was interested in predicting power consumption in, for example, a country. It depends, depending on the zone, other parameters. But I really couldn't find any data set or any public data set, because there is a lot of private data sets, but you don't have access to them. So my question is, do you know any reliable source of data set that is free available for research?
I'm putting resources in the chat. You should go to our wiki, and if you navigate to the power systems part of the wiki, you can find whatever data sets we know about in that area. And you can also ask a question in our community platform if you want to find more information. We have the experts in power systems on that forum.
So
there is some data publicly available across different geographies, but I would point you to that compendium.
Okay. Thank you very much for the meeting. It was, as I said, very interesting.
More questions from the audience? No? Daniel Molina. Please, Daniel, go ahead.
Okay, do you hear me?
Yeah, sure.
Yes, I can.
Okay, thank you first for the nice presentation. It's very interesting also because I was working in a work looking for ways in the machine learning for improve the change of the climate, and it's very important that it's very nice to work in that type of topics. And I'm curious about something, because I was a little worried about what you talked about the ImageNet, because usually we use pre-trained model by ImageNet, but usually with several problems that they are not very similar to detection of animals. So it's not important for us. Maybe that is not well accurate, and there is no.
I'm not sure what effect that'll have in that context.
Yeah, but now we have in a project in which we want to use specifically this data set to identify animals in a national park.
Yeah, don't do that. Use these data sets.
Yeah, what do you suggest? We should do retraining for specific animals like a snake, or you should
I would use the iNaturalist data set.
Okay.
I wrote it in the chat. That would be probably the best match for that particular setting. What are they particular kinds of animals? Is it just birds? Is it how are the photos being taken? Are they being taken by individual people? Is it a camera trap?
No, it's detected by individual people from identify which is the animal that are take more picture in the natural park. It's more a study about it.
Do iNaturalist.
Yeah. There is pre-trained models using that database, or okay.
Yes.
Thank you a lot.
Absolutely.
More questions?
iNaturalist was annotated by expert ecologists. So and it's also just much bigger. It's actually it's designed as a fine-grained data set specifically for animal identification. So that should be good.
So any other question? No? Well, I have a quite naive question, David.
Sure.
I don't know if you could comment on the fact that self-driving cars will make climate change worse. I don't know if you can extend your ideas.
Oh yeah, I mean, again, I was looking to, so going back to my slides here, what I was talking about is like, it depends on how we build autonomous vehicles. So personal vehicles, personal self-driving cars, the best estimate that people can make is that they will make each mile driven a little bit more efficient because they can drive more efficiently, but the barrier to driving will be reduced. People will want to drive more. They also maybe buy more cars. So there will be more embodied emissions from cars, and there will also be just more miles being driven. So it's expected that those factors will counterbalance any slight savings per mile driven, just because there are more miles being driven. So if there is more vehicle sharing or more public transportation, that could counteract that. But right now, that's not the way the technologies are being developed. And the problems that are being prioritized in the field are very much focused on personal cars. So if we change the problems that we're working on as technologists, that can potentially help shift towards uses of the technology that are ultimately better from a climate perspective, at least.
Yeah, sure.
Yeah.
Totally agree.
And I want to distinguish, obviously, between autonomous vehicles and electric vehicles. Great to electrify cars, but they don't have to go together.
Yeah, exactly. Absolutely. So any other question? Because otherwise we can close here this DaSCI seminar with David Rolnick.
Okay. Thank you so much. It was a pleasure joining you all.
Yeah. Okay, well, thanks again, David. It was an amazing talk. And let's keep in touch, of course.
Absolutely. Take care.
Thank you to everybody. Take care.
Bye.